So now let's talk about torque. To make an object rotate, so we've been talking about rotational objects. So now we have to figure out what is causing the object to rotate. So to make an object rotate, a force must be applied on the right place. A combination of force and a point of application is called torque. So basically, torque is a measure of how much force acting on an object causes that object to accelerate. So now let's talk about it a little bit more. So let's say you have a rod and it has a pivot point or an axle, which is also called the axis of rotation, which in general we will call 0 or O. A force is applied at this end. What do you think it will happen? So it's fixed at the axle and the rod is kind of let go. So now you're applying a force on this direction only. And it's free to rotate about its axis, right? So in general, what you will find is that that object will start to rotate. The point of application of the force and the axle point is going to be called the lever arm or the moment arm, okay? And note that the distance r, or the moment arm or the lever arm, whatever you want to call it, is a vector, and it points from the axis of rotation to the point where the force acts. So let's say if we were to apply the force here, the moment arm would be this much. If we were to apply the force here, the moment arm will only be this much. Also, since the force and the moment arm are vectors, we have to be very careful about the angles in between them, and we'll talk about that in a second. So torque mathematically is going to be given as r cross f, where r is a vector and f is also a vector. And the relationship, this is a cross product between the moment arm and the perpendicular force, so that will be given by rf sine theta, where theta is the angle between the moment arm and the force applied. By convention, when the applied force causes the object to rotate in a counterclockwise direction, that is when torque is called positive. When the applied force causes the object to rotate clockwise, then the torque is called negative. One of the reasons which might help you understand why that convention was developed was because think of what the positive angles are. So the angles that go from the reference line that way are called positive angles. So the torque sort of simply follows the same convention. So now let's look at this simple problem, okay? So if you have a nut or a bolt and you want to tighten the bolt, well, what are the possibilities? Let's say you apply the force as shown in this animation right here. Now, what will this force produce as a torque? So obviously it will start to move this wrench over this way. So the line of action of force for this particular example is going to be here. Now, the moment arm you would think would be here, but actually it's not. The moment arm is the perpendicular distance between the applied force and where the axis of rotation is. In this case, it's that point right there. So in this case, the torque will be F, which is applied force, times L1. What if you were to apply the same force that way? In this case, your line of action of force will be shown by that dotted line, and your moment arm or your lever arm will be L2. In this case, it is actually at 90 degrees and it's easier to see. So the torque will be F2 times L2. Now note, as I am going down, this torque is going to be bigger than the torque that was with the force that was at an angle. What about if we have a cheater's pipe in here? So somebody wants to cheat. What can he do? Well, if he's going to apply the same amount of force, but he's going to increase his pipe, the length of the pipe. So what he's doing is he's basically increasing his moment arm. In this case, the moment arm is the largest, and the force is being applied at 90 degrees, which is absolutely perfect. So the torque will be the greatest. Why? Because in this case, L3 is bigger than either of L1 and L2. Interesting. On the other hand, the flip side is a rotating spinning object will continue to rotate unless it is acted upon by a torque. So now my next question is, where on a door would you push to open it? Will you push here? If this is the hinge, if you push here, 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 where? Where is the most likely point to push where you would get the most torque or the least force? So the idea is that you can either apply a large force or a small distance, or a bigger distance but a smaller force, and that is called mechanical advantage. So if you have a wrench and a nut that you want to tighten, if you hold the wrench here, you will need a lot of force in order for the screw to be tightened. But your hand doesn't move very far. However, if you hold the wrench here, you don't need as much force. However, but your hand will move a long way in order to cover the same angle. So again, it depends on whether you have enough force or whether you have a smaller distance to cover. So now let's talk about how to calculate the value of torque. Say you have a force, so say you have a top view of the door that we were talking about. If this is the end where the hinge is, and you are applying a force in this direction, that force is going to have two components, the parallel one and the perpendicular one. So we know torque equals R times F, which is perpendicular, where R is the distance from the axis of rotation to where the force is applied. And F perpendicular is the component of the force that is perpendicular to the door, which is going to be this one. So if you were to calculate what this is going to be, this is going to be F perpendicular, or F sine theta, as a component. On the other hand, the second method will be if you were to consider the lever arm to be the perpendicular one, and you leave the F as the magnitude of the applied force. In this case, what you will do is same picture from before. Now this is going to be your R. Note that this is not what your lever arm is going to be. But what in this case you'll have to look at is the line of action of force, right? So you know that if this angle is theta, this angle is also theta. So this means that your lever arm is now going to be the one that is going to be perpendicular to the line of action of force. Okay, there's going to be only one point when you would connect the axis to the line of action of force where the angle will be completely 90 degrees. You could make it go like this and the angles will never be 90, or here or here. This angle has to be 90 degrees. In this case, you will now have sine theta equals R perpendicular over R, if you were to draw this triangle like that. So that means your R perpendicular, the one that you are looking for, is going to be R sine theta. If you plug it into the torque equation, torque equals R perpendicular F, and the answer will come out to be RF sine theta, which is exactly the same as the one we used for method 1. So for both cases, your final answer should come out to be the same, whether you use method 1 or whether you use method 2. Now, what happens when you have more than one force, let's say, acting on an object? Well, in that case, what you will need to do is you will need to define what net torque you have. So the torque we know is equals to R times F perpendicular, which means it is RF sine theta. So just like we had the sum of forces, we are now also going to have the sum of the torques, right? So let's say in this example, there are two forces acting on it, F1 and F2, and they are opposing forces. One will cause the object to rotate this way, and the other one will cause the object to rotate this way, right? So if you were to write the sum of all their torques, that is going to be the torque due to force 1 and the torque due to force 2. In total, the torque due to force 1 is going to be given by F1 D1, where D1 is the lever arm for the force F1, minus F2 D2, where D2 is the lever arm for F2. Now the Y is 1 plus and Y is 1 minus. And remember, clockwise, we said clockwise torques are negative and counterclockwise torques are considered positive. That is what that shows up in your equation here. So now let's look at a few cases where torques are either applied or not applied. So the first case is going to be where there are two forces, and consider the axis of rotation to be in the center. So one force is being applied this way on the bar and the other force is applied this way on the bar. If you notice that the net force in this case is going to be 0 because one equal and opposite forces are going to be acting on it and nothing will happen and the object will remain exactly at rest, so net torque will be 0. So now the next case is going to be net force is not equals to 0. In this case, one force is being applied this way and the other force is being applied on the other way. Now note very carefully, if these bars were allowed to move, they will move up and down. However, they will not rotate. Now case 3 is where there are two equal and opposite same forces, but they are being applied to this point and this point. They are acting against one another. So in this case, if you were to think of the forces acting this way, they are acting and they are going to rotate your object that way. Okay? This means, yes, there will be a net torque in the system and the rod will rotate. Okay, so if the object is in equilibrium, it doesn't matter where you put your axis of rotation for calculating the net torque. The location of axis of rotation is completely arbitrary. Often the nature of the problem will suggest a convenient location for the axis. So when solving problems with torques, you must specify an axis of rotation. It's almost as important as specifying the origin for linear motions. Once you have chosen your axis, you must maintain that choice consistently throughout the problem. So how does torque help us balance a beam? So let's say you have a beam and it's, imagine it's a seesaw, right? And it has two sides on it. It has a pivot point in the middle, and you put a 10 Newton mass on one side, which is about 1 meter away. Now, where should you place another mass, which is 20 Newtons, in order for your torques to balance, in order for this beam to stay balanced? Yes, you need to put it at a 20 Newton mass at half a meter away, so that when you multiply 10 by 1 and you multiply 20 by a half, the torques become equal. Once the torque becomes equal, then they are a balanced force and the beam will be balanced. This is a very good idea for you to know this for your lab. So left torque equals 10 Newton meters, right torque equals 10 Newton meters. These two forces are balanced.